And I guess I need that. Thank you. I thought I'd have the ideal of no electronic, the purely, sort of Renaissance technique for lecturing, but I guess that's not completely acceptable. So I guess this is the first taste of a sort of, quote, experimental physics in this series. I'm not an experimentalist, I'm a theoretician, but I like to talk about and think about experiments a lot. And this will be, this will get us into superconductivity. So it's rather a deeply condensed matter subject. And I'm conscious of the sort of heterogeneity, or I want to just sort of get a sense of the heterogeneity of the group here. All of you obviously are interested in quantum information science. How many of you work in condensed matter subjects? Right, so about half. And how many have never taken a condensed matter lecture in their life? Ah, yeah, see, that's my problem here. But not to worry, because, okay, here's my third quiz question. Did you all, in high school, learn about this thing? I hope, yeah, all right, great. So everybody knows what an inductor is, and that will be pretty much enough. That is, what superconducting qubit, the ideas of superconducting qubits are really built on ideas more of electric circuit theory than really of superconductivity. You need to know, I mean, it wouldn't work except for all of the details of superconductivity, but me giving you the basics of the theory, you'll more need to know, or we'll need to remember what this symbol means, more than knowing about, the fourth order fermionic correlator in the superconducting state. But actually, that's what I'm going to start with. So just to set up a few of the important ideas, I do want to state a deeply quantum mechanical fact. But then we're going to be doing classical physics for quite a while. Oh, I'm holding this paper actually only because it has my outline of my 3 days of talks, of lectures. Rather than actually put it on the board, I'll just say it in the words that today I'll review a little bit of the state of the field of this subject of superconducting qubits. I'll make my necessary deeply quantum mechanical statements about superconductivity, but that will get us rather quickly to some phenomenological laws, or I'll discuss them as phenomenological laws, key facts about how superconductors behave that make it possible to make kind of versatile electric circuits out of them that in turn can be quantized. And that's about as far as I'll get today, perhaps. I may also just, by the end, I may be able to tell you sort of a set of sort of neat qubits. Once we've got sort of the basics of electric circuits in hand, then you'll see the variety of fairly simple electric circuits that we quantize. And I'll continue with that tomorrow morning. And so a lot of tomorrow will be just devoted to how they work. They are electric circuits, we can quantize them, but how do they work as qubits? So we'll do the transmon, and we'll do the phase qubit. We'll do a few of the famous gizmos that people are working with these days. We may even do the 0 pi qubit. I don't know how ambitious I'm going to get about that. And we'll talk about how they're measured, how they're initialized, and also the ways in which they are decohered. And then in the third lecture, I'll get to a very popular and gigantic subject of the present time, which is called circuit quantum electrodynamics, which gets us in turn to the way of how you build towards multi-qubit systems. And so in that lecture, I think I'll get to quantum gates, basic control methods that are used to do high accuracy quantum gates. And then finally, I'll end with sort of scalable architecture things, because I'm basically, my life since the mid-1990s has been sort of a dream world of big quantum computers. So, and somehow I remain in that dream world, and maybe someday the dreams will become real, but at least we continue to articulate ideas about that. So that's the whole set of 3 lectures until the end of this week. Now, the state of the field, again, I think I'll just do only in words, because you can just read the popular press, I mean the pages of Physics Today or the front pages of Science Magazine or whatever, and just see that people are doing great things or talking about doing great things. But in reality, this subject has come from a side branch or a part of solid-state physics, of solid-state device physics in the 1990s. One of many ways of exploring small electronic things, and then with the ideas of qubits, there were the first sort of glimmerings of qubits in those systems with very, very poor coherence. But over the last decade, the subject has blossomed with every year showing a big factor increase in how much coherence as qubits you can achieve with them, until in the present time, the qubits are about as coherent as anything that are used in atomic physics. Not quite, maybe, but quite competitively, and with a lot of a big toolkit of techniques and many possible ideas for the future, which may or may not succeed for actually building larger systems. Okay, but as I promised, I'm going to begin. Okay, so we have to do superconductivity. We have to know a little bit about that. Although, if any of you looked at the homework problems that I rather quickly posed, I formulated one which is more sort of a discussion thing that I don't think I'll get to, but which points to the fact that we're going to begin with electrons and Cooper pairs and things like that. But in fact, the whole premise of superconducting qubits would not have to be played out in that way at all. We could start with bosonic condensates, and at least in principle, the whole story could go through. So I posed sort of a discussion homework of design a superfluid helium-4 superqubit, leave out the word conducting. And that seems all possible in principle. The Josephson effect has been seen in helium-4, and well, gravitational potentials replace the capacitive potentials that we'll be discussing today. It's probably all very implausible and unlikely, but I mean, that would be the hard work to show why it's not what people are doing, and it's really in the details rather than in the broad principles. Okay, so let me make a statement about what is superconductivity to me and what it should be, in getting started in superconducting qubits. So it has to do with my blackboard will be a metal, will be a sea of interacting fermions, usually 3-dimensional. There's no reason to be low-dimensional in this subject. So we'll talk about a 3-dimensional world, and so there will be at low temperature some quantum state of those many electrons, and we will discuss a particular property that quantum state has that distinguishes it from copper or gold or something, or that is to say metals that don't superconduct. So to do that, I didn't quite leave enough space, so I'm actually going to write one matrix element, in fact, of that quantum state. And I should say that this will imply that I'm talking about what this thing does at 0 temperature, but it will actually be true also for the Gibbs density matrix of this state up to some reasonable temperature. But I'll do it this way for simplicity. So let's do the following matrix element. I apply an electronic creation operator. This is a fermionic operator at position, in the notes that I have here, R4. I'm going to write what I mean by that in a moment. So that's really a field operator. Usually you'd write phi or something like that, but I have too many phis in my world. So I'm going to put a position R4, so it's a creation operator at position R4. There's also a creation operator at position R3. And there's R3. And then somewhere rather far away is position R1 and R2. And I'll apply destruction operators at those positions. So R1, R2, R3, R4, destruction, destruction, creation, creation, that matrix element. So that probes a feature of this wave function. And now, by design, I've put these pairs of points rather close together, but them as groups well separated, far separated from each other. And now, in a normal metal, this would be very small. That is, if I pulled these points very far apart, this would be sort of exponentially small in this distance. So copper, gold, aluminum above 2 degrees Kelvin. But for a superconductor, it's not small. And it can be written in the following way, that there's some function of the positions R1 and R2. These are intended not to be far apart, but there's still some dependence on how far they are apart. Some basically identical function of the other two coordinates. Normally one would put a star here, but I'm actually going to pull out the imaginary part of this explicitly, or the complex part of this, and say it's times an additional phase, e to the I. Now we have phi of, let's say, R1 minus phi of R2. Okay, end of statement. And as you see, it has no dependence on, except for this phase, has no dependence on how far apart these are. So they can be separated to, quote, infinity, as far as I'm inside, as long as I'm inside the conductor.
Wait, the phase only depends on R1 and R2?
Well, okay. So I'm taking an approximation where this distance, which I didn't label, well, so R1 minus R3 is much, much bigger than R1 minus R2. And so I'm approximating this. So I'm fuzzing out things at that length scale, because these functions are, in fact, there's no sense in separating these by very much, because it turns out these do fall off very fast. So these have some exponential factor, e to the R1 minus R2 divided by coherence length. So that's one of the important physical properties of the superconductor, coherence length.
But there's no phi of R3 minus phi of R4?
No, well, okay. This is a, quote, short distance, so these never get very far apart, or there's no point. If you put them far apart, the whole thing is zero. So the main phase dependence is between this pair of positions and this pair of positions. So think coarse-grained enough that those are the... Oh, did I screw up already? Oh, I screwed up already, sorry. This is my Blackboard dyslexia coming in. Thank you very much. Sorry. Okay, so everyone's happy again, I bet.
Should the fraction be inside the parentheses of phi?
What should be inside the parentheses of phi?
It's a question. Should the R1 minus R3 be inside the parentheses of phi?
No. But I have some more comments about that. Because the conventional route, okay, so this is superconductivity. The fact that this is this so-called off-diagonal long-range order. LRO, long-range order. And it is the big fact that distinguishes it from ordinary conductors. And it's the phenomenology mostly of these phases that actually make for it being very different as a beast compared with ordinary conductors. So let me say a few things about that. So I've already mentioned that these are typically short-ranged, although short is not necessarily so short. I mean, coherence lengths go from sort of atomic scale dimensions in copper oxides to, 100 nanometers or something, not very small, in so-called weakly coupled superconductors. We're not going to get into any of that. We'll deal with situations where this is all effectively zero, where the coherence length is very small compared with all the sort of device dimensions in the problem. It is conventional to then separate these out and say, well, in some sense, this is factorizable into an expectation value of this pair of operators, sitting here, times an expectation value of this. And you see the factors here. I can associate that with this. And then this is often just referred to as a complex number delta, complex function delta. I don't want to go there. I mean, there's a vast, lengthy discussion about whether that makes any sense. And it's connected to the question, what's the broken symmetry of the superconducting phase, which I also want to stay away from. To me, this is adequate. This is satisfactory, and no one would disagree with this statement as given. It is. It agrees with BCS theory, and it doesn't come along with all necessarily other baggage that BCS theory comes along with. Now, it should be said that this phase difference, it does sort of imply that there is really objectively a phase of the state associated with, this point. I'm joining these together and saying that's one point, coarse-grained. That is a possible but definitely not necessary point of view. The only thing that really ever matters, and you know quantum mechanically that it's the only thing that should matter, are phase differences. So, we will loosely talk about, and people even not so loosely, or at least at length, talk about the phase of this superconductor here. And that's maybe not so wise. It's always better and never necessary to go beyond the idea that it's differences of phases at different places in conductors. And, you can apply this idea not just to a homogeneous superconductor, but now sort of zooming out, if you had, a piece of superconductor that's sort of shaped, let's say, like this. I'm not doing this completely at random. This part's a little bit at random. And then there's a part here that sort of meanders back and forth, a solid piece of superconductor. It's indeed perfectly fine to think of, R1 and R2 are here, and R3 and R4 are over here. And indeed, because there is a superconductor connecting them, there is indeed a definite phase relating this point, this pair point, to this pair point. And I've drawn sort of a piece of an actual present-day superconducting qubit, so this is not a trivial or meaningless exercise. So this idea, this microscopic idea, applies also to these macro complex objects that we call qubits. And the phase variation, or the dynamics of this phase, which I will get into, is in fact the key point. Another observation, this is obviously, as stated, a C number. It's just something that characterizes a matrix element of a state. I might confusingly, let me at least use a different color. I might confusingly put in here some symbols like that, put in an expectation value up here, and put in maybe hats to indicate that, well, I'm going to also, maybe without much change of notation, elevate these phi's to quantum numbers, to Q numbers, in Dirac's language, as we go on. But for a while, they will in fact be classical, and we're going to kind of re-quantize them. We're going to recognize that they are intimately associated with another operator, with another quantum operator, which will be a phase operator, and whose Heisenberg equations of motion, whose quantum dynamics will closely mimic the classical dynamics, or will be a reflection of the classical dynamics that we've deduced for these. Okay.
Can I just interpret this as saying that there's a field that creates these bound states which has an expectation value? It looks like, so like C dagger is like a creation operator for the pair R3, R4.
Yeah.
And then this correlation function is factoring because it's saying that field has a one-point function.
Okay, I think that's, you said the word bound state, which confused me.
Well,
I'm sure it's the string theorist and me, a condensed matter physicist, basically every third word we mean in a different way. So we have to be very careful here. But I think what I also heard was the idea of factorization, which is that I could put some little things in here.
Yeah, that's
and yes, exactly. Now that's what I was mumbling about a moment ago, that it's conventional to say, yes, this operator has a finite expectation value. you know, that pair creation operator, that anomalous field. And I don't, well, I say that's not necessary. There's no reason, no need to talk about it that way, although it leads you to very easy ways of thinking about this state, indeed.
It looks like you're violating cluster decomposition, which is weird, right? So then it's usually that's because there's some one-click function.
Okay, I also barely know what that phrase means in this.
Stuff should fall off at large separation.
Oh, yeah. Well, okay. Well, that's broken symmetry. Well, okay. I mean, then people would say, oh, then obviously it's because it's broken symmetry.
Yeah, by the expectation value of C dagger.
Yeah. Okay. I mean, I'm not going to solve this problem. I'll just say that, you know, Phil Anderson says, yes, what you just said is all correct. And, you know, the essence of this is a U1 symmetry breaking. And Tony Leggett has a whole book that says, no, that's stupid. You know, electrons are electrons, and you know, they're conserved. And you know, if you have an operator that creates two of them, you get a new quantum state that's orthogonal to the other one. So, or sort of super selection ideas. And it's not for me, humble me, to say which of those giants is actually correct. So that's why I wanted to say the barest minimum. That I think is undeniably correct. But at least I wanted to expose you to that discussion because, I mean, this idea of saying, you know, this superconductor, I don't have a nice piece of metal here, but, you know, this superconductor, it's not really, has a phase and it's 3 degrees, you know, and that would be a kind of conventional thing to end up saying. If you believe that this genuinely has an expectation value, then it means that things objectively have these phases. And that's what's unnecessary, although somehow very natural for many people, but really unnecessary, because we only ever talk about the phase difference between this and, you know, my transmon. Okay, now, next subject is what if we've got 2 of these superconductors? And this already gets most of the story. I mean, well, we'll have to do a bunch of work to talk about the dynamics of these, but that'll get us to inductors and things like that. But the key thing, and actually it's often the title, that is, instead of superconducting qubits, you hear Josephson qubits, because in fact the Josephson effect is sort of a crucial phenomenon, or the phenomenology described by Josephson, is really at the heart of how you can versatilely make qubits. So let me do that, just finding the page where I have that written for myself in the best way. So what a Josephson junction is, let's see, now I'm completely confused about how to effectively use these.
Just don't move them, push them to the side.
Just, okay. And I have this sort of vestigial board, as epsilon board to work with. But okay, I'll try it that way. So okay, Josephson effect. To do Josephson effect, we need 2 chunks of superconductor. Okay, that's a piece of aluminum or something. Here's another piece of aluminum, and they happen to get really close somewhere. So now all the things I've said are true without change, in fact, for this whole system, but there's going to be some special things. So in other words, I put my 4 points here. Fine, there's some phase variation. But one principle will be that if you're in a big solid piece of superconductor, the phase tends to not change. So the phase tends to remain constant. The phase difference tends to remain 0 throughout this region. So until further notice, we'll just say that this region acts as if it has 1 phase, which I could call 0 because I haven't, I'll set some phase reference, let's say. So this is chunk A of aluminum, this is chunk B. And in here, similarly, I could do this stuff. And phase differences throughout this region are also pretty much 0. That will get changed, in fact, only when we extrude this into long, long wires and call them inductors. So this has also pretty much all one phase. We'll call that phi b. And indeed, these indeed also, there is a definite phase difference between these, which is phi a minus phi b. Now, I've put these really close, and the point of that is they're close enough so that now microscopically electrons can in fact tunnel. There's a term in the underlying Hamiltonian, which I'm otherwise or indeed abjuring from writing down ever in this lecture. But there is a term in that mythical Hamiltonian that will hop electrons, will destroy fermions on one side, create them on the other with some kind of reasonable amplitude. And that is a Josephson junction. So this region is called the Josephson junction. Oops. And now I just have to state the two observations that Josephson made about this setup that will get us almost everything else. I should say this is sort of turns out to be a specialized part of a much vaster phenomenology of superconductors, which is sort of under the heading of London theory. London was a scientist who actually figured out basically everything about how superconductors must be without really knowing this. So his book is somehow very confusing to read. It's from 1940-something. But he sort of got all the phenomenology straight, and he knew there had to be phases involved, and he had sort of the right rules for them, and he knew also how it relates to electrodynamics, which we're going to do in a baby way. So, for example, when the Bardeen-Cooper-Schrieffer discovery came about, their paper in 1957, it's clear they did that work with a very deep knowledge of everything that London had written down. And for them, that was sort of inseparable. They had to get all of that right, all the phenomenology right. But today, somehow, BCS and the post-BCS is easier for us in the present day to completely comprehend. Okay, so Josephson noted this, or wanted to say things about this. Now, what he discovered were two laws, which I'll just motivate, but I won't derive. Let me just make sure I state them the way I have them written here. So he noted, I'll put them up here, because Josephson's laws, so his laws, J's laws, number one. If there is a phase difference, phi a minus phi b, if there's a non-zero phase difference, then there is flowing a supercurrent, so a dissipationless electron current. And that supercurrent, however, is some interesting function of that phase difference, so it's a sine function of that phase difference. So let me slightly motivate that. It has some prefactor constant, which is sort of an ordinary, I'll call it device parameter, this critical current. It's obviously the maximum current that is permitted in this law. It's an ordinary sort of extensive thing, that is, you double the area of contact, you double the current, you make the tunneling stronger, you bring them closer together, the current goes up. There's actually an exponential law involved in that. But it's a macroscopic parameter, just like an inductance or a capacitance. Now, this sine function, let's talk about that. So I can at least convince you that if these phases are all the same everywhere, which actually means that this factor is absent, and then this correlation function is completely real, which implies this wave function is completely real, which implies that it's time reversal symmetric, which means there shouldn't be any currents. So at least that's a little bit of an argument for why when phases are all the same everywhere, there shouldn't be any currents flowing, just on basic symmetry principles. And the other thing is, obviously, adding 2 pi doesn't matter to these. I say that obviously, but I'm actually going to come back to that. There's some unobvious things about that totally obvious statement. So in the way I've set things up here, phi b or phi b plus 2 pi shouldn't matter. So this should indeed be periodic, 2 pi periodic. Now, those two facts do not imply a sinus function. And in fact, there's actually nothing so fundamental about this law. So I could write, there's no conventional, there's no real notation for this that I'm familiar with, but IC prime sine of, let's say, 2 phi A minus phi B plus, etc. Such terms are totally allowed and sometimes actually even big. And there are certain detailed conditions which happen to be met by sort of most Josephson junctions that people make, including the ones that were first grown, fortunately, to test Josephson's ideas, in which these higher harmonics happen to be small. So we will, but as you'll see, they're also pretty harmless. I'll cross them out, but they're totally harmless, actually. If they're there, I can still make very good qubits. They don't disturb things. They disturb my analysis a little bit. I mean, when I come to actually saying, you know, I do the following, solve the following Schrödinger equation, and the qubit frequency is 3.8 megahertz, or no, it would be gigahertz, I may be needed to take, or I would have to think about whether terms like this were present to really make predictions. So that would be a sign that this one macroscopic parameter wasn't quite enough to capture everything quantitatively. But qualitatively, it's perfectly fine. Okay, so that's one law. Law number 2 is something about what happens if you do something that has not yet been talked about. Here you apply a voltage between these two pieces of superconductor. Now that seems like it's slightly a no-no, or everything's supposed to be without voltage drops, and now I'm applying a voltage. So the system doesn't like that. And what it does is it causes these phases to start racing around in time. So the specific formula for that is h bar over 2e. Time derivative of phi a minus phi b is equal to the voltage. Now I woke up early this morning thinking about this law because it was very natural to say, and you derive it by doing the following. And there's actually all sorts of kind of derivations of this, and there's one that comes, very much from this London direction. And but if you look up Feynman lectures, is a totally different looking derivation, which basically just says the following: that if you it invokes or it states that it just comes directly from the Schrödinger equation. I think this is actually correct. That if you had no voltages anywhere, and the Hamiltonian with the right constants chosen has a ground state energy of 0, so there would be then, if you solve the time-dependent Schrödinger equation, no time change of the phase of the state. But if you apply a voltage, then you've sort of pushed something up. You've added a constant, basically, to the energy of the eigenstate of this whole system, and so the phase in the time-dependent Schrödinger equation is starting to run with that added energy. So that's the way Feynman stated it. And since, I said that I would stay at undergraduate level. Oh no, I said I would stay at high school level. So surely at that level I could stop and say Feynman told us that that was the right answer. I think that's actually not incorrect. And in fact, it's clear to me, although this is where thinking about it at 6 in the morning, I couldn't bring together all the arguments for why this is so, that this is actually quite fundamental, unlike this, which has, some corrections are possible, but this is really kinematic somehow, that this is not susceptible to corrections. Okay, now indeed we're about to go high school on this. That is, well, not really, but definitely very classical and we'll depart, these fermions and quantum fields and stuff will recede into the background for pretty much the whole rest of the story. Because there are just now some observations to make, first of all, about the Josephson junction itself.
David?
Yes?
I just wanted to make one comment since you had mentioned London and DCS and also Leggett and Anderson. I was told by somebody who was in the editorial office of the American Physical Society that Josephson's article was rejected by the referee, who said it was completely ridiculous. He was taking this notion of the phase as something physical too seriously, and it's now known that there's an underlying microscopics of electrons, and it has to be described in terms of that. And so the article was complete nonsense. And the question is, who is the referee?
Oh, do I have? Was it Leggett? No, it was too long ago.
It was Bardeen.
Oh, Bardeen. I see. Okay. Yeah. Okay. Well, Bardeen certainly was of the school that says you factorize and then you learn all the physics. Okay, you do learn all the physics by factorizing, but you maybe lose some of the concepts. I mean, for me, in the year 2014, this is the way that this is the reality of the phase, and for me, this is good enough. The fact that it is an expectation value, a very robust, rigid expectation value of a quantum state. Okay. Yeah. Interesting. Okay, so let's get to how we're going to build circuits based on this. But I need to make one more statement, which I could have made right at the beginning. There is really one piece of quantum physics that's important to not leave aside, which is that this... yeah.
This expectation, is it something observable?
Yes. I should warn, though, that it's connected with what I'm about to say, which is that it's not quite because it's not gauge invariant. But without that, well, I can fix that, and then we can have things that were no problem with the gauge. But yes, I mean, well, I stopped to think for a moment because each of these is independently. I mean, there are ways of getting at the amplitude of the order parameter, and thinking about that. And this phase is very, very manifest, has huge sort of macroscopic consequences when you build these superconductors into the right forms. So I think that amounts to saying, yes, it is an observable. I mean, you worry, this is not a Hermitian operator, so it's maybe a little bit nasty in that regard. Okay, well, let me not get too deep into that. I mean, many people would say that just this the thing which I wrote, let me actually write it out since I've been saying it so often, that we can talk about this matrix element, C of R1, C of R2. So that even that matrix element would be, from many people's point of view, observable. Its phase can't be, we will say, but that gets us into the Bardeen confusion. Its amplitude, I'd argue, yes, is quite readily knowable. Okay, that's a good question. Let me not keep this here. Okay, gauge dependence, because we really need that. And London knew all about this, actually, also, which is that if I change gauge, this stays the same, but not this. So, so I'm going to write another arrow with the word gauge on it. So what happens if there's a vector potential? You go to a gauge. Actually, we're going to be mostly in gauges which are magnetic field free. Because of Meissner. I mean, you can try putting a magnetic field inside these things. Good luck. Let's just stay away from that. Let's always but we'll put magnetic fields elsewhere, in the vicinity of these conductors, and that can make a difference. So there is a gauge. Well, no, I shouldn't say it that way. So I may need vector potentials, but well, they're what is it? They're curl free, I guess, locally. So it's reasonable that this phase difference, phi r1 minus phi r2, will have to be augmented by a factor, and that factor is minus twice e over h bar, I guess. The line integral from R1 to R2 of the vector potential, dr. Okay, and then, as I say, we will need that. That's important that if you change gauge, it'll be more the point that we will encounter situations where we need
R3.
oh, hell. Yes, thank you. So you think that the lectures just sprinkle in these little mistakes to keep people awake. But for me, it's not true at all. I just very naturally make those mistakes, don't even notice them. Okay, so that's a rule that we need to remember, or we'll actually apply very shortly, that if there is a vector potential, and that will happen very soon in situations like this. So blob of conductor, two places where you have Josephson tunneling, and here you can put a magnetic field, and here it really matters. And so there will be a line integral, non-zero line integral of the vector potential around that loop. And so we have to put that vector potential somewhere. But this formula will be convenient because then wherever we put it, we'll know how to take account of it. Okay. So that was indeed one other bit of quantum physics we really needed. Okay, but now we're going to form an interpretation of these laws that'll be helpful in moving towards electric circuits. So first of all, first observation is that this whole object, so the phases and this prefactor have the physical units of Webers. In other words, it has the units of a magnetic flux. I won't derive that, but it's true. And so this should then highly resemble, oh yeah, see, in Germany, we have these sensible blackboards where you just do this, and the board goes up like this. But okay, doesn't work here. So let's just pretend, let's use a symbol, so magnetic flux, symbol capital Phi. This is taking you almost back to high school, although I actually couldn't remember. I think you learned this in high school. That you have now another equation that looks kind of familiar, phi dot equals V. So that's Faraday. And indeed, the phase will in many respects behave just like a magnetic flux, except for, h bar over 2e, which needs to be thrown in. But the dynamics of the phase will be very much like the dynamics of, remember I drew this for you? And that, this relation, well, this is true explicitly for an inductor, that the time variation of the magnetic flux threading the inductor, let's see, am I saying this right? Is in fact the voltage. So, so this will start to look familiar, and we're actually going to transit temporarily to completely classical electric thinking. Maybe I'll throw in, although I don't especially need it at this point, that this prefactor has its own symbol. So h bar over 2e is actually phi 0 over 2 pi. That just simply defines what's called the, what is it called? The quantum of flux. Or as some friends of mine have referred to it as phi 0 bar, like h bar. But it's rather hard to put the bar anywhere onto the phi 0. So, so we're kind of stuck with that. So that 2 pi often is there explicitly. Okay, so in fact what I'm coming to is what's the relation of this to an inductor. Okay, now I'm going to attempt this trick. I'll probably regret this, but let's see. Okay, so a Josephson junction as an inductor. So in fact, the point will be that Josephson laws are indistinguishable from that, or tell you that the Josephson junction as a two-terminal device is an inductor. Now this sine function doesn't look very much like an inductor, but let me explain a little bit. So in electric theory, I mean, that is to say, if you started life as an electrical engineer and you learned things that way, the electricians have or the electrical scientists have a formal statement about what they mean by an inductor. And it doesn't actually involve just the symbol L. It says that something is an inductor. I'll write it this way. It's sometimes written this way in the literature. There's sort of a little sign thing, but it just meant that it's not linear. So it says there's some functional relation between, I'm leaving a little space here, between the current flowing through this object and its associated magnetic flux. Now, this is actually kind of formal, so and in fact, we'll find cases where there isn't a symbol which is a magnetic flux, but you can't explicitly identify it with a bundle of magnetic field lines. And so for the electrician, the flux variable of this two-terminal device is merely something whose time derivative is the voltage. So for them, that's sufficient formal meaning for a magnetic flux. So I can put anything else I want here. So that somewhat fortuitously anticipated the Josephson situation. I mean, I don't know of any other case in electrical science where you use this equation and this isn't, a genuine true blue magnetic flux. Let me emphasize the non-trivialness of this by putting in time arguments here, because in fact that is what makes it special, that it says that the instantaneous value of this variable is, there is a functional relation between the instantaneous value of this and the instantaneous value of the current. That's really what makes it an inductance, rather than something with capacitance or something like that. And furthermore, the key point about an inductor is that it stores energy. And does not dissipate it. And interestingly enough, that's true no matter what this function is. So now, of course, if the function if f of x is x over L, so it's a linear function, then you can confirm that that's indeed where that's the place where you put this macroscopic parameter, the inductance in henries. But in fact, we have a different situation here. But let me write down this idea of storage of energy. So again, I think back in high school, I maybe learned that the way you figure out how much energy is stored in this thing is that you integrate the current times the voltage over time. And you actually, you have to do things to take, if energy is continually disappearing into this thing, then you call that dissipation. But if you find that it's, if you put it, you go through the right cycle, it will all come back at you. That's a sign that it's merely stored and not dissipated. But let's work this out. So that's equal to, I'll call this U temporarily for energy stored at time t. The idea is you ramp up, you start from an unenergized situation, no current, say, or no flux, and then current rises as a function of time because of some external influence. But notice that I can substitute in here 0 to t, I. I'll do, there's f of phi, there's d phi dt, and there's dt. And so I learned in 12th grade that you're supposed to do that. So, so that this is supposed to be, so this indeed is just the integral, so the area under this function up to, let me write one more line, up to the flux of interest, that can be interpreted as a stored energy, as a potential energy. And that word is going to get me back to mechanics after a while and get me even back to Schrödinger equations and things like that. But I'm far, far away from them at the moment. Okay, let's do this for this function. So for example, if I have a linear inductor, integral 0 to phi, phi d phi over L, 1/2 phi squared over L. Sound familiar? Okay, so it's a quadratic or harmonic function. The energy stored is a harmonic function of this variable, of this state variable, this flux. Okay, but we have another example, right? Which is that f of x is I critical sine function of, now I'm just thinking, do I want to use, yeah, now I'll go over to, so I need to throw in this 2 pi over phi 0. I just have symbol phi, but what that whole combination is indeed just phi a minus phi b. It's if this is a Josephson junction. So let's do the integral in that case. Maybe I'll skip a step because I think you can do this integral. But I'll even keep the constant temporarily. So this IC phi 0 over 2 pi. And then there's a 1, which we can throw away pretty soon. Cosine of, well, I'll go back to phi. Just to save a little bit of writing. It is just still a phase, meaning a phase difference, right? Phase difference across it. This prefactor often gets called E sub j. So it has units of joules of energy, so it's a Josephson energy. But it's just the same as this critical current. It's just another, in different units, the macroscopic parameter, scales with the area and so forth of the Josephson junction. Now here, well, I wrote here somewhat superfluously that I really mean phi minus 2 pi over h bar, I believe, integral a dot dr. Now, but I mean, well, maybe it should look a little strange that I even bring this up at this moment because the Josephson junction is by construction a very tiny thing in the sense that, let's go back to my picture. I think it's still here. Yeah, good. Whoops. So the line integral of the vector potential that we're talking about in this situation is from here to here. Now, did you got that? It's not far. I mean, these things are about 4 atomic layers thick, the ones that you make out of aluminum. So you have aluminum, you puff a teeny weeny bit of oxygen onto it so that the very little bit of oxidation occurs, and you dump a bunch of aluminum back on top of that. So you would think that any sensible vector potential in such a teeny line integral I wouldn't care about. But that's where the gauge will come in. And in fact, there's a very convenient gauge where I can't ignore that at all. And that's why it's worthwhile to keep it there. And in fact, I'm going to use it in my very next construction. So we're actually going to construct a device now. We haven't even gotten to the conjugate variable yet, the one that stores, this stores magnetic energy. You want to also store electric energy. You want capacitors. But even without capacitors, I can already do the first interesting exercise based on this construction. So that will be the what's called the Dc Squid, which is possibly one of the worst namings in physics that you could ever imagine, because it's the DC is just totally irrelevant to anything that we talk about, and squid is also a real abomination. I mean, they couldn't help it. It was back in the 60s or something, or 70s. So squid, does everyone know what squid means in this context? Oh, no. Okay, so we don't. Good. I mean, your mind is pure then. That's very good. But I guess I should pollute it just slightly in order at least to denigrate the heresies. So, well, I'm going to See, this is where I get completely confused. So now we're going to do the following electric device. I already drew it, but I'm just going to draw it in more circuit way. So there's a two-terminal device, just two Josephson junctions in parallel, maybe with, indeed, a magnetic flux passing inside this loop. So this is the thing that's called the DC, for direct current. Squid. Squid refers to superconducting, no objection there, conducting, quantum, sort of okay, interference, oh boy, device. So that acronym is SQUID. And the SQUIDs are actually quite useful instruments. They are, the point is they're actually very, by sort of ordinary standards, they're very, very sensitive to the magnetic field you put here. And so they're actually very good sensors of magnetic field. So even though, they have to be operated at low temperature in order for things to be superconducting, there are still, situations like in cases where you want to image currents that are flowing around inside the brain, that there are these instruments that come down to the poor patients whose brains have to be studied, which are filled with arrays of these squids. And they map out, by measuring these electric currents, you measure the magnetic fields, and you map out what's going on inside that poor person's head. So that's a real technology. But the objectionable part is mostly this, that especially in this room, this is really wrong, because this is not a quantum interference. It's not it has nothing to do with, some kind of interference occurring in the quantum phase of the state. It's actually an interference connected with this variable, this flux, this phi variable. Well, I've already said it's a C number. But it's something that obeys kind of a wave equation, classical wave equation, essentially. Classical wave equations can have interference. So I would have really called this a skid or something, because it's sort of really classical interference at the level that we're talking about. Okay, but since your mind was pure, so okay, forget all that. Yes? Well, are you talking about this or now just the single Josephson junction? Okay, this you make, let's see how concrete I want to be. This is okay conceptually, two lumps of aluminum that you've arranged to have touching with a space, with a gap in between. Maybe it's an appropriate moment, since you ask it, to say, well, what are people actually doing? What is this in the laboratory? In the laboratory, you grow, I said it's aluminum, sometimes niobium, but it's not many other metals. So you grow with some electron beam gizmo, some little finger of aluminum. And you could do that, okay, put a little finger over here, put a little finger over there. The length scales of this, so this is on some insulator, which will be hopefully doing nothing, but unfortunately the insulators do bad stuff a little bit. But it's on some inert thing, and you just make a little U-shaped thing of aluminum. The scale of this is maybe 15 nanometers, so it is valuable. I'm getting, maybe not today, to the point of what's the interesting scales of these numbers, because we want to get quantum eventually. And you could make this be 15 centimeters of aluminum. Aluminum isn't that expensive. But you'd end up with really big EJs, and that would be bad for actually making things quantum in a reasonable way. But it turns out this scale, which is not atomic, it's many, many atomic widths wide, puts us in a very good range of length scales. So anyway, think this 150 angstrom width wires, which you make by E-beam lithography. And then it's this thing that I just said, you puff in a little bit of oxygen, so it's all corroded slightly. But to the very slightest extent, it doesn't matter that it's all over the place. And then you start over again, and you grow on top of that some kind of bar of aluminum. Same process. And then you contact it, let's say. That could have been part of the whole story to begin with. So there it is. That's my two-terminal device. And that is a DC Squid. It's not yet a qubit, although it's really close. I mean, it can already be a qubit. Let me put it that way. But usually you want a little bit more for your device. Okay, now, okay, so I was going to do this device. And so the important thing is that these energies are additive, basically. Again, I'm just invoking classical facts that this stored energy, you have a stored energy here, you have a stored energy here. Now, I'll write loosely, you know, in electrical theory, you'd write, okay, 0V voltage, and you'd put a little ground symbol here or something. You have some reference point. I'll also think of that as my reference point of phase. So I have a 0 here, and I have a phi over here. But I have to be careful about that, because I am going to put a magnetic flux here. Okay, so let's write the energy function of this. So let me erase over here. Okay, so right. So the energy of this guy is EJ. I have a 1 here. EJ1. There's junction 1 and there's junction 2, and maybe they have somewhat different macroscopic parameters. They don't have to be the same. EJ1. I need a minus sign here. Cosine. I just called it phi. And I have minus EJ2 cosine phi, except not. Well, sorry, I haven't done the flux yet. I can't put phi here. But I can do the following. I have to choose a gauge. And the only point about this Aharonov-Bohm flux is that the line integral of the vector potential around this loop has to be I guess phi over, now I'm confused a little bit, 2 pi phi external over phi 0, if I've got my constants right. So this is phi external. So I'm really applying some number of Webers to this structure. And so I have to put this vector potential someplace. And it turns out the best place to put it is here. Put a little cut here. And I pass it straight through that, 1 nanometer so gap and out. What I mean by that is that I make the vector potential 0 everywhere except it's a delta function on this cut, basically. So that it will, when I pass my line integral through this point, it will integrate through that appropriate delta function and pick up the right line integral. And by doing that, it sort of gets me immediately into the sort of the usual coordinate system. It means that then this is not phi, but it's this gauge invariant phi, or this, it's the phi that you get from using this particular gauge. So it's 2 pi phi external over phi 0. So, and that's, and I guess I could have put the cut somewhere else, but I haven't really given a rule for what's happening. I would have had to put in rules saying the phases are allowed to jump inside bulk superconductors, and it's sort of convenient not to have to do that. So that's that's the energy function. Now, the hardest part is to use what you really learned in 10th grade or something, and do the trigonometric reduction of this. Let me actually write it out, because I went to the trouble of rewriting this. With Mathematica, even with Mathematica, this is hard to do. You use trig reduce, trig expand, x to trig to x, simplify, full simplify. It never gets to the expression I'm about to write. So it proves human beings who went to high school are still smarter, sometimes, than computer programs. So this is equal to a quadrature. So it's EJ1 squared plus EJ2 squared. Plus twice EJ1, EJ2, and then the cosine of, let me abbreviate all of this stuff to call it phi 0. It's all in the square root. And then it's times a single cosine phi minus, again, there's some other thing, phi prime. Phi prime is some arctangent of, oh, it's too boring to write, but it's just some offset that I get by doing combining these two cosines. The important thing is just that the result is still a cosine, so except for this sort of offset of the phase, this is still behaving like a single Josephson junction. It has the same dynamics as a single Josephson junction, but it is, however, tunable. So there's no real symbol for that, but there's you have a little knob here that lets you dial up stronger or weaker Josephson coupling, including if if EJ1 equals EJ2, and you put half a flux quantum through this, then this prefactor goes to 0. So you can actually turn off the Josephson coupling. You can actually make it an insulator, basically, just by application of a magnetic field. And that tunability is actually very valuable, or has been valuable, in constructing qubits. Because, well, you have a qubit, you'd like to change its energy. The energy depends on this indirectly. I mean, you have to solve a Schrödinger equation, actually, based on this as a potential. But you turn your knob, and that changes the potential landscape and changes the energies. So that's been a valuable quantum control tool. It's actually not as popular as it used to be. I mean, used to be, this is now all, prehistory is before the year 2000. So this is all kind of recent history. But from maybe 2005 on, this has tended to get a little less prominent as the control method of choice. And the reason for that is, so this is bad because, sorry, I'm putting this so low. I'll put it up here. Bad potentially because of what's called flux noise. Because of flux noise. Now, there's a whole phenomenology to the fact that the magnetic field here, I mean, it is, you have a coil outside the experiment, and, it applies some number of Webers here, but there's all sorts of other stuff going on. There's the Earth's field, trivial, you shield that out. Even the Earth's field itself has some fluctuation, but you shield that all out. But still, there's other stuff going on, and in fact, it's mostly implicated that they're actually basically atomic spins that are occasionally flipping nearby. And that's enough to change the amount of flux passed through this loop by tiny amounts, by 10 to the minus 4 or something of this fundamental flux quantum. But that's enough. That's too big from our current point of view. That's too much noise to live with. As I say, I may get into some of the phenomenology of that. I mean, it matters that on what timescales those fluctuations occur. Because if they're slow enough, you can get rid of them by quantum control techniques. Okay, but blah, blah, blah. There's a whole, really, story based on that. Now, I want to come back to something which seems totally obvious. So I had this picture here, and it could be just for the single Josephson junction. And I've already commented that, obviously, this is all 2 pi periodic in this phase. And so it would be natural to make as a general principle that, well, this will play the role of a mechanics variable. We're going to do some real classical mechanics, Lagrangians and Legendre transformations. Not very much of that, but some of that. And so it's relevant. It's important to know which of your variables are compact and which of them are non-compact. And this looks like an obvious compact variable without even much thinking about it. But that's not actually true. And whether this is compact or not, however, depends not on this itself, but on what it's attached to. So let me give an example. So it turns out the dynamics of this object, a single Josephson junction, if I do one more thing, and well, I'm getting to that, but let's for the moment note that there's another contribution to the energy of this thing, that there's a capacitor as well. That this is actually identical in its mechanics to a regular clock pendulum, including the cosinus part of the law. And so indeed, coincidentally, not coincidentally, the phase angle of this pendulum is just exactly the phase that's relevant in the Josephson junction. And so yes, of course, this is 2 pi periodic. And so this looks compact. Now, I'd like to say that that has something to do with what we're getting to in quantum physics as well. I mean, eventually we have to associate a Hilbert space with these things. And the thing is that you say, this in its resting position is an element of Hilbert space. And in fact, any displacement of it is an element of Hilbert space. But and when it gets all the way around again, it's exactly the same as it was. So that's the same element of Hilbert space. But let's make one change. Let's put a little coil spring here. So that has nothing to do with the pendulum itself. But if I whip the pendulum around once, then I've coiled, maybe this is a very weak spring. Let's make it a very, very, very weak spring. But still, it has a winding number. It has a number of turns. And it will actually it will record physically how many loops you've made, even if it makes a negligible contribution to the energy. So it's the addition of that turns phi into a non-compact variable. So now it is meaningful all the way from minus infinity to infinity. So in writing down the dynamics for these things, one requires a kind of global examination of the system, of the circuit, to know whether even something you call a phase is or is not 2 pi periodic. There are even more, well, I'll mention this, but I would rapidly run out of gas anyway. It's even so that sometimes this is appropriately 4 pi periodic. But those are more exotic. Then we have to do Majorana things. Unfortunately, I'm not doing Majorana stuff in my lectures. Okay, so we're almost at a point where I can announce all sorts of fun qubits to play with, except I didn't do capacitors yet. So let's do capacitors briefly. Capacitors are what you remember from high school. So yes.
What is the electric circuit equivalent of this string?
Oh, sorry. It always happens. You erase it and then immediately it's needed. Yes. In fact, it's not surprisingly from the way it looks. It's an inductor. That's exactly the circuit element that will play that role. So if I put a regular discrete inductor here, that's the spring. And indeed, the phase, an inductor violates the rule that the phase remains constant inside a solid conductor. Phase can or does, inductor, you say, so to speak, is so long and thin that the phase can slowly twist as it goes from one end to another. And so it can accommodate some number of twists. I mean, there's a whole science of so-called phase slips in physical inductors. But if you make them out of a thick enough wire, they can accommodate many 2 pi's of twists of the phase. Okay, so as I said, let's do capacitors. And I have no idea why I'm holding this sheet at the moment. I know I have a sheet that says all sorts of great things about capacitors. Let's see. Okay, I'm not seeing it at the moment, no problem. So remember, a capacitor is something which you can describe in several different ways. It has a charge and a countercharge, so we'll call that Q. And there's a voltage across it, and Q equals CV. So voltage difference, charge accumulated on the capacitor, and one new macroscopic constant, capacitance in farads. And so even these things already by themselves have capacitance. You know, here I showed this cartoon of how you actually grow these things, and you know, it is indeed a parallel plate capacitance, so it has a bit of capacitance itself. It's mostly, certainly in current qubits, not enough capacitance, so you actually add some capacitance. That sounds strange because the capacitance, again, referring to the pendulum I erased, the capacitance actually is the mass of the pendulum. And you'd think heavier is worse because it's more classical. But it turns out that this is maybe a little too quantum. So it's actually better to load it a bit and make it a bit more classical. So the circumstances are that you actually add extra capacitance. Okay, so now let's do energy storage. Now, this is where I know I wrote down some story. Again, I can make it up myself, but let's take one time derivative of this equation. So I get back to a current. Current is C times V dot. Now we do energy storage. Call it a quote kinetic energy. T is integral IV dt. Same kind of stuff. We'll not do nonlinear capacitors, and there aren't any that that we really have at our disposal anyway. I mean, the electrical scientist was very happy. Again, there's some function as long as Q and V have some instantaneous functional relation. That's enough for the electrical scientist for it to be a capacitance. But we don't need that here. So we have a C outside, and we have V dot, well, V times V dot, dV dt. I'll do this again so I have the pleasure of doing a little cancellation. And there we have 1/2 CV squared. And this, in fact, will be what we use to finish our story. That is, for the simplest qubit, which is indeed this, we're done with our accounting of energies. And this, if you'll note, if I bring back, or if I just introduce a phi variable, phi dot squared. Now, what's that phi? I mean, where's the flux? And this is one of these cases where I say there isn't any. It's a formal variable. It's a formal state variable whose time derivative is the voltage. That's the meaning I attributed to it. If there is a capacitor in parallel with this, then I can indeed associate it with that variable. So, but this is the form that we will use. So this here I can actually use some notes here. Because this is the way in which you would write this energy in order to immediately write a Lagrangian for this system. Because I have 1/2 C phi dot squared, and I have plus or minus or something, sorry, I'm not sure which, but we have something which is, well, it's just called plus some function of phi, and meaning not a phi dot, but that's like this cosine or phi squared or whatever. And this is indeed, in mechanics, the right form, is a function of the state variable and the time derivative of the state variable. So, and we could with Feynman, we could right away do quantum theory straight away. We'd start quantizing, but we tend to adopt a Hamiltonian view, in which, well, we're going to want to write this. We want to do a Legendre transformation and write a Hamiltonian based on this. So we have to identify a conjugate variable. I'm not going to do that formalism. I mean, you'll have to go remember your formal mechanics. That you didn't learn in high school, I know, but somewhere in your second year in university or something. But recall, though, that in the electrical world, you often just rewrite this, plug this back in, and in this situation, it's nothing more than that, except for one extremely important complication, which I'll come back to. So I plug that into here, and I get q squared over 2c. C goes downstairs, and that in fact is the essence of the Legendre transformation in this case, and the q is indeed functioning as the conjugate variable. It's the appropriate, it's the derivative of L with respect to phi dot or something like that with some replacement of variables. And so I can have a Hamiltonian. Now, okay, there's an important complication. Yeah.
The energy was integral over function f, right?
Well, sorry, I didn't mean this to be the function f. It's just whatever function I had come to after, I'll call it u of phi or let's call it u of phi. That's actually better. Sorry, I didn't mean to confuse things by using the same symbol at that moment. So it's really this u that I've been developing, like here, for example. That's the appropriate energy function, energy storage function of the circuit. Yeah, okay. My minus sign dyslexia comes again. That's a little worse because I personally don't use Lagrangians that much since I'm not a particle theorist. So these minus signs always leave me a little cold. Okay, one important thing that very important for qubits is that this law is wrong. Well, I said we weren't going to do nonlinear, and we're not. We're going to keep it linear, except in real life there's something called Q offset. Now, there's nothing so weird about that. It just means that it can be that, well, I would normally put it on the other side, I guess. That is that if the applied voltage is 0, there can still be some charges there that are not influenced by the applied voltage. And why? Because they're just, bound charges, basically. Well, there's several possible reasons for it. But there are actually, the material is charged, that it holds bound charge that is not polarized by the applied voltage. It can also be, it can also originate sort of intentionally if you put a voltage source, if you put a battery across this in this way with another coupling capacitor, that will also, from the point of view of this capacitor, offset the sort of 0 charge. So, and that really comes here, that I would write, instead of Q squared, I would write Q minus Q offset squared. But Q offset will remain a C number in this discussion. Although that's not absolutely a given. It depends, if the charge has to do with some bound charges, that there actually may be some quantum aspect to that we need to take account of. But it's often not the case. It's often that it's just stuck there. It unfortunately varies slowly in time, so it's a source of so-called charge noise. Another arrow, charge noise. And so there was flux noise. This is really a killer, though. You have to take all measures possible to not be sensitive to this noise, because this is, for this kind of stuff, this is not an absolute statement, but for this kind of, aluminum, evaporate, blah, 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 that this charge noise is significant. It really makes a difference, and it, many E's worth of noise, generally not very fast in time. That is, this C number, therefore, is like a C number function, Q offset, meaning a function of time. So, and here's the scale E, 2E, etc., 3E. And, and let's do the scale of seconds. That's fine. It's over some time, it's not doing very much, and then it does something like this, and it does something like that, and it really is a problem, because it, it actually has, a diverging spectral weight at 0 frequency as a 1 over F spectrum, so it really is problematic. So you want to, so it is there. Actually, the material scientists are gradually getting better at dealing with this, but it really is very much materials cleanliness and not having defects and not having instabilities at interfaces, and the least bit of junk will get you right back to where you started from. So it's much better, and fortunately there are qubits where you just don't care. It just is this thing's fluctuating away, and it is in the Hamiltonian. This is a term in the Hamiltonian, but it just doesn't affect things, just because of the way the qubit is designed. And I'll come to why that is so tomorrow, I guess. Now, okay, I have a few more minutes, but I won't plunge into really any other significant, serious efforts at this point. But let me say that this toolkit that I've now introduced is the whole toolkit. That with this you can announce, the whole universe of superconducting qubits. And I thought it would be fun to give you a little sketch of all the possibilities. So some of them we've already been sketching, but maybe I'll attach names to them. So for the rest, I'll just this will be just a taxonomic exercise for the last 5 or 10 minutes, just to attach little circuits to names that many of you probably heard. So this thing is in fact the phase qubit, which has had its day. I think it's run out of steam. It's not such a popular qubit at this point. Oh, sorry, I'm already saying the wrong thing. A phase qubit is well, it was the second one I was going to mention. The phase qubit is something that does explicitly have an inductance, and where the magnetic flux through here is important. Yeah.
You call these devices or circuits qubit.
Yeah.
But when you say qubit, for me it's 0, 1.
Yeah.
Set.
Okay.
In what sense these are qubits?
That's really a good question, because there are whole vast crowds of people. You go to a conference with 500 people, and they're saying qubit, 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 and they only mean this. So it's a real linguistic problem that there are whole communities that use the word qubit for a physical device which could embody a qubit in meaning one sense, in the dictionary. So we haven't come to that yet. I mean, I have to now re-quantize. This is all classical physics, including the stuff about Lagrangians and Hamiltonians, but I now have to re-quantize or elevate the status of these classical state variables to operators and solve for the quantum dynamics, and find that they do have energy eigenstates which I can conveniently associate with 0 and 1. So very good. Yeah, but it's a massive disconnect, although not a very dangerous one, because we can usually tell from context whether there's somebody standing up with grease on their hands saying qubit, that they mean that. Whereas if Scott stands up and says qubit, he certainly doesn't mean that. So
That's for sure.
maybe with me you'd have a little trouble. I don't know.
Can you just say in that circuit again, which parts of that are actually superconducting?
Everything.
Everything. So
Yeah. So.
all the wires are superconducting. The X is the Josephson junction.
Yeah. So this is indeed one continuous lump of superconductor.
The inductor is really like
Well, the inductor, yeah. Well, that's a good question. There are cases where you make single spirals of this thin film wire, and you have to reconnect it over. You have to sort of bridge over. So it turns out it's sufficient to make an inductor. Let me sketch this whole object as a piece of lithography art. So it turns out it's sufficient to make an inductor to just make a long meandering wire. And so that's the inductor. Then we come back over here. And then there's this place where there's this tunneling contact, or tunneling possible. And then, for the phase qubits, sometimes they did, sometimes they didn't. Then had an additional structure, which is like this. being careful not to make contact or even to be particularly close. So that's a capacitor. It's a so-called interdigitated capacitor. These are the digits. So there's a large perimeter of contact, but still the distance is kept fairly large. There's no tunneling in the Hamiltonian. There's this little bitty place where the two parts of the conductor are brought very close, so that, with this few atoms of oxide in between, so that there is, in fact, tunneling contact. And then this is just made long enough so that the phase, even though it's very stiff, is capable of twisting, actually quite a few 2 pi's throughout this wire. And this whole thing could be maybe 100 micrometers in size, which is sort of remarkably big, because this is really a good 0-1 qubit. But you can basically, well, with your magnifying glass, you can actually see the thing. Of course, when you're looking at it, seeing it, it's not a very good qubit. You better shut it up. You better not have all those photons hitting it. These are very sensitive to photons. Actually, a big difference between this, although we've gotten sort of pseudo-atomic, it's actually there is still a lot of awkwardness associated with the following fact: that if I have actually an atom and I ask what's its energy states, you've seen all these pictures where you have this stuff and blah blah blah, F's and J's and things. So you have some states, and you can find some of them that are qubit, and you say, where's the next state? Well, it's somewhere up here, and there's some laser energy, some optical frequency corresponding to that. So that's atoms. And what we'll have with qubits, with superconductors, is sort of the following. We get, indeed, by the right design, we get sort of interesting manifolds of low energy states. But the trouble is, about 2 orders of magnitude lower than the first energy, sort of the next energy, we have a whole continuum. So starting in the far infrared, there's the next excitation, but then there's the next and the next, and it's extremely dense. There are potentially quite a lot of levels here, because as you'll see, you actually do implement sort of continuous variable quantum bits in this system. So it's not that there are negligible numbers of qubits, of states here, and of course, if you're in a quantum computer, you want exponentially many here. But this is sort of a denser, divergently large number of states, starting already at 100 gigahertz or something. And that's painful, because it means you have to, if you have radiation going by, which happens to be of this frequency, far IR, you've killed this qubit. So it has to be kept really, really dark. Whereas if you're doing a beryllium ion, this thing's up in the ultraviolet, and you can have the room lights on, no problem. So that's definitely a technical difficulty of using these things. And it means, you have to keep them cold. That's sort of a given. Aluminum only superconducts at about 1 degree Kelvin, so you obviously have to be lower than that. And that's okay. People know how to do that. That's getting more and more, doable thing. Or I wouldn't say routine, but a lot of people can do that. But it has to be cold and also dark. They put on all sorts of blocking of all sorts of radiations that must not go down into this cold space. Okay, so there was a big digression. Now, you know what? I have now a cartoon of, I think, about 10 qubits in this sense. But I'll leave them for tomorrow. We'll start tomorrow with our catalog of qubits, and then we'll pick one or two of them, and actually analyze them, and actually get the information theoretic qubit out of the physical qubit by solving a Schrödinger equation, basically. Okay, any other questions, thoughts, whatever? Yeah.